Have you ever really stopped to think about what happens when, say, a device needs a sudden big burst of power? Like think about a camera flash. Bang! It lights up a whole room instantly, hundreds of watts.
Yeah, huge power for a split second.
Or, something much more serious like a defibrillator, that massive jolt to restart a heart. How do we actually store that kind of energy so it's ready to go instantly without just, well, fizzling out?
Right. It's a really fundamental problem, actually, in electronics. For ages, if you managed to get some electric charge onto something, like a metal ball, it would just leak off into the air or poof, gone the second you touched it.
Yep.
The real challenge was, how do you hold on to that charge reliably and then let it go exactly when you need it in a controlled way?
And that's where this device comes in.
That is precisely where the capacitor comes in.
Right.
It's kind of the unsung hero here. It's designed specifically to store electric charge on a structure, ready for later use, getting around that old problem of the charge just disappearing.
Okay, let's unpack this then. Today, we're really going to dig into the world of capacitors. We'll look at their design, which is surprisingly simple, actually.
Remarkably so.
How they work their magic, and why they're basically everywhere in modern life. So, just starting out, what does a capacitor look like, fundamentally?
At its core, it's incredibly simple. You've got two conductive plates, sometimes called armatures, basically the metal bits that hold the charge.
Okay, two plates.
And they're separated by a small gap, an insulating gap, that's key. Think of two pieces of foil, close, but definitely not touching.
Got it.
Now, when you connect something like a battery across these plates, that's when the charging process starts.
Right.
The battery, it provides the energy, pushes positive charges onto one of those plates.
Okay.
And then at the same time, the free electrons on the other plate get repelled by those positive charges coming in. They move away, leaving that second plate with a net negative charge.
Ah, so one positive, one negative.
Exactly. And what's really fascinating, the crucial bit, is that the insulating gap stops them from just jumping across and neutralizing each other.
But they want to, right? Because they're attracted.
Oh, absolutely. There's a strong electrostatic attraction between the positive plate and the negative plate right across that gap. And that attraction is what keeps the charges sort of trapped there, stored on the capacitor, just waiting.
I can picture that. They're stuck wanting to get back together. It sounds like it must get harder to add more charge as it fills up.
It does, yeah.
Sort of like trying to pump more air into a balloon that's already pretty full.
That's a great analogy, actually. It gets progressively harder. And eventually, you reach a point where the capacitor can't really take any more charge from that specific source.
How does that happen?
That happens when the voltage, the potential difference across the capacitor plates, becomes equal to the voltage of the battery that's charging it. At that point, the pushing stops.
But you mentioned voltage. What happens if you try to push too hard? Like, use too high a voltage battery for a particular capacitor. Does it just stop charging, or is it worse than that?
That's a really important practical point. No, it doesn't just stop. If you exceed the capacitor's voltage rating, you risk something called dielectric breakdown.
Breakdown. Sounds bad.
It is. The insulating material between the plates, the dielectric, basically fails. It stops insulating and becomes conductive.
Oh, so it shorts out.
Effectively, yes. You get a short circuit and often a very sudden, sometimes even dramatic release of all that stored energy can be quite forceful, even explosive in some cases. So yeah, paying attention to voltage ratings is absolutely critical for safety.
Okay, good to know.
Yeah.
So assuming we charged it correctly and then disconnected the battery, what happens?
Well, connecting back to the bigger picture, those charges don't just vanish. Because of that strong mutual attraction we talked about, they stay put. Held firmly on the plates by that electrostatic force, just patiently waiting for a way to get across.
And that's when they become useful, when we give them that path.
Exactly.
So if you connect, say, a light bulb between the two plates.
Or the coil for a camera flash, or the paddles of a defibrillator.
Yes.
You provide a conductive path.
And then
those positive charges, which are so strongly attracted to the negative ones, they rush through that path, through the bulb filament or whatever it is, to meet the negative charges and neutralize.
And that sudden rush of charge is the current.
That's the current. That rapid flow is what lights the bulb, powers the flash, delivers the shock. It's also why they're crucial in power supplies, for smoothing out ripples in voltage, turning choppy DC into a nice, steady flow that sensitive electronics need.
Makes sense. Almost everything needs steady power.
Pretty much. That rapid controlled discharge is indispensable. But, this raises a key question.
Which is,
How do we actually measure or quantify how much charge a specific capacitor can hold? They're obviously not all the same size or capability.
right. And that property, its ability to store charge, that's what we call capacitance, isn't it?
Wait. That's the term, capacitance. It's the fundamental intrinsic property.
So how is it defined precisely?
Okay, so capacitance, we usually use the letter C for it, is defined as the amount of charge, which we call Q, that a capacitor can store for every unit of potential difference or voltage across its plates. We usually write that voltage difference as delta V.
Okay.
So the formula is C equals Q over delta V. Make sure you get that right.
C equals Q over delta V.
Got it.
And the unit?
The unit is the farad, symbol F, named after Michael Faraday, who did tons of early work with electricity and magnetism. He apparently loved demonstrating Leyden jars, which were early capacitors, sometimes giving volunteers quite a shock.
Ah, I bet. So 1 farad means what?
1 farad is equal to 1 coulomb of charge stored per volt of potential difference. So 1F equals 1 C per V. Again, that's coulomb per volt.
1 coulomb per volt. And a coulomb's a lot of charge, right?
Oh, huge. It's the standard unit, represents a massive number of electrons. That's why you usually see capacitors rated in microfarads or even smaller units in practice.
Right, like picofarads.
Exactly. And it's really important to remember the capacitance value itself, the C, that's fixed by the capacitor's physical construction. It doesn't change if you apply more voltage.
Ah, okay. So applying more voltage doesn't change the capacitance.
No, what changes is Q, the amount of charge it stores. That increases proportionally with the voltage, but C itself stays the same for that device.
Okay, that makes sense. So if I pick up a capacitor and it says 1 microfarad on the side, what does that mean in practice?
It means for every single volt you apply across its terminals, it will store 1 microcoulomb of charge. That's 1 times 10 to the minus 6 coulombs.
Okay.
If you put 2 volts across it, it'll store 2 microcoulombs. Put 10 volts, it stores 10 microcoulombs. But its capacitance is still stubbornly 1 microfarad because you haven't changed how it's built.
Right. Its physical nature dictates its capacitance.
Precisely. So if capacitance is intrinsic, fixed by its design, what physical things actually determine that value?
Good question. It must depend on how it's made.
It absolutely does. It depends on its geometry, its shape and size, and also on the material between the plates.
So you're saying we could actually calculate the capacitance just by measuring the capacitor?
For simple designs, yes, definitely. Let's take the most basic type. The parallel plate capacitor, like our 2 pieces of foil.
Okay.
First, the surface area of the plates, we call that A. And crucially, it's the area where the plates overlap. If one plate is bigger, it's only the common area that counts.
Makes sense. More area, more storage space.
Exactly. Second, the distance between the plates, we call that D. Let's get into it. Where do we start?
Well, the basic definition, right? Capacity C is just the amount of charge Q you can store for every volt of potential difference, delta V, across the plates.
So C equals Q divided by delta V. Simple ratio.
Simple ratio, yeah. It's intrinsic. It depends on the physical setup.
Yeah.
The area of the plates, A, how far apart they are, D, and, well, what's between the plates.
Okay, so how do we show that Q, the charge, doesn't actually set the capacity? How do we get it to sort of disappear from the final equation?
Right, that's the core of the derivation. We need to connect that delta V, the potential difference, back to the geometry.
How do we do that?
Through the electric field, E, remember for parallel plates, the voltage difference, delta V, is just the electric field strength. E multiplied by the distance, D between the plates.
Oh, okay. So delta V equals E times D, step 1.
Step 1. Now, what determines E? The electric field itself.
Doesn't that come from the charges on the plates?
It does. Specifically, it comes from the surface charge density, sigma. The field E between the plates is sigma divided by epsilon 0.
Sigma over epsilon 0. And epsilon 0 is that constant for free space, right? The permittivity.
Got it. It basically tells you how easily an electric field can set itself up in a vacuum.
Okay, so we need sigma now. What's sigma?
Sigma is just how spread out the charges. The total charge Q divided by the area A over which it's spread. So sigma equals Q over A.
Q over A. Okay, I think I see where this is going. We're building a chain.
Exactly. Now we substitute, take that expression for sigma, the Q over A, and plug it into the equation for the electric field E.
So E equals, instead of sigma, we put Q over A. So it's Q over A divided by epsilon 0.
Now take that expression for E.
And plug it back into the delta V equation. Delta V equals E times D.
Yes,
0.
exactly. Delta V equals QD over A epsilon 0. See? We've now linked the voltage directly to the charge Q and the geometry A and D.
Right. And now for the final step, we go back to the start.
Back to the very definition of capacitance. C equals Q divided by delta V.
And we substitute our big new expression for delta V into the denominator.
Do it.
Q times D over A times epsilon 0.
Yes.
And look at that. There's Q on top and a Q inside the fraction on the bottom.
And what happens when you divide by a fraction?
You multiply by the reciprocal. So it becomes C equals Q times A epsilon 0 over QD.
Bingo. And now?
The Q cancels, Q in the numerator, Q in the denominator. They just go away.
They cancel out. And that's the magic. That cancellation proves that C, the capacity, doesn't depend on Q, the charge you happen to put on it.
It only depends on what's left.
Which is?
C equals epsilon 0 A over D.
There it is. Capacity is determined solely by the plate area A, the separation distance D, and that constant epsilon 0 for the space between them.
Wow. Okay, so breaking that down for someone, say, designing a capacitor.
It tells you exactly what to tweak. Want more capacity? Increase the area A, make the plates bigger. That's why capacitors can get physically large. Or decrease the distance D. Get those plates closer together. Since D is in the denominator, making it smaller makes C bigger.
And that's probably harder to do physically, getting things really close without touching.
That's often the challenge, yeah. Especially when you also want to handle high voltages. But the relationship is clear. Bigger A, smaller D means more farads.
So the capacity is fixed when it's made. The charge it holds just depends on the voltage you connect it to.
That's the key takeaway. The capacity is baked in.
So here's a thought then. If capacity is so tied to physical size, A and D, what does that imply for making really powerful electronics incredibly small? Are we hitting fundamental limits based purely on geometry when we need lots of capacitance in like microscopic spaces?
That is precisely the challenge engineers face every single day. Miniaturization versus fundamental physics.
Fundamental.
Okay. Now, in real circuits, you don't often find just one capacitor sitting alone. They're usually connected with other components, sometimes with other capacitors.
Very true.
So how do they behave when you connect them together? Let's start with putting them in parallel. What happens then? Side by side, connect to the same points.
Right, parallel connection. In that case, the key thing is that the voltage, the potential difference delta V across each capacitor is exactly the same.
Okay, same voltage on all of them.
And it's equal to the total voltage across the whole group. Now, the total charge stored by the combination, let's call it Q equivalent. That's simply the sum of the charges stored on each individual capacitor. So Q equivalent equals Q1 plus Q2 plus Q3 and so on.
Adding up the charges makes sense if they all see the same voltage.
It does. It follows that the total equivalent capacitance, C equivalent, is just the simple sum of the individual capacitances.
Ah, so C equivalent equals C1 plus C2 plus C3.
Exactly. Is that this is the complete opposite of how resistors add up when they're in series.
Oh, right. Resistors in series add directly. Rec at R1 plus R2.
Correct. But capacitors in parallel add directly, C equals C1 plus C2. It's easy to mix them up. The way to think about it for parallel capacitors is you're essentially increasing the total plate area available for storing charge. More area, more capacitance.
That's a helpful way to remember it. Okay, so that's parallel. What about putting them in series, one after another in a line?
Series connection. This works differently. Here, the total voltage across the whole chain of capacitors, delta V equivalent, is the sum of the individual voltages across each one. So delta V equivalent equals delta V1 plus delta V2.
Okay, voltages add up this time.
But, and this is the crucial part for series forge, the charge, Q, stored on each capacitor in the series string is identical.
Wait, the same charge on each one? How does that happen?
It happens through charge induction. Imagine the battery pulls electrons off the first plate, leaving it positive, pushes them onto the last plate, making it negative. That positive charge on the first plate attracts an equal amount of negative charge onto the second plate, its partner.
Okay.
Which means an equal amount of positive charge must have been repelled from the other side of that second plate, moving on to the third plate, attracting negative charge to the fourth, and so on down the line. It's like a chain reaction.
Ah, I see. So the charge has to be equal all the way down the chain. So if the charges are equal but the voltages add up, how do we find the equivalent capacitance, C equivalent?
The reciprocal of the equivalent capacitance, that's 1 over C equivalent, equals the sum of the reciprocals of the individual capacitances.
Okay, hold on. So 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. That looks familiar. That's how resistors add up in parallel.
Exactly. See, it's completely flipped compared to resistors. Capacitors in series add like resistors in parallel, and capacitors in parallel add like resistors in series.
Right, okay. That's definitely something to keep straight. Why does series reduce the total capacitance like that?
You can think of it like this. Putting capacitors in series is effectively increasing the thickness of the total insulation, the total distance the charge separation has to span across the whole chain. Increasing the effective distance D reduces the capacitance.
Right. Increasing the separation reduces C.
Hmm.
Okay, that helps visualize it. So pulling all this together, what does this really mean for you, listening at home, in your day-to-day life?
Well, it means these little components are everywhere doing critical jobs.
From the really tiny ones,
Hmm.
filtering noise in your phone's circuit so you get clear audio,
Mm-hmm.
to the ones ensuring the timing is perfect in your car's engine control, or smoothing out the power from a wall socket for your computer.
And of course, back to those high-power applications like the camera flash or the defibrillator we started with, they are the silent, essential workhorses.
They might look simple, just those two plates and a gap,
Deceptively simple.
but their ability to grab energy, hold it, and then release it quickly, or to filter signals, it just makes so much of our modern tech possible.
Absolutely. There's a real elegance, I think, in how this simple structure solves such a fundamental problem in electricity storing charge controllably. And understanding these basics, how the geometry matters, how they combine in series and parallel, it really gives you insight into much more complex stuff.
It unlocks how things work under the hood.
It really does. It lets you appreciate that constant dance of charges happening inside almost every device you own.
So maybe next time you hear that click, or see a flash, or even just look at your phone screen staying perfectly steady,
Yeah.
give a little thought to the capacitors inside. These tiny components, patiently storing and releasing energy second by second, making it all work. And maybe ask yourself, what other really simple but incredibly powerful physical ideas are working away silently in the objects we use every single day?